Welcome along, explorer. My name's Dan. It's the part of the week where we're a little bit bored of life down here on blue-green planet Earth. So let's see what else is out there, shall we? And search for some science secrets across the universe. It's the Fun Kids Science Weekly. And this week we're settling the ultimate Earth-sized question. It's grain of sands versus drops of water.
Surely, there's much more water than there is sand. The Earth is over 70% water. The Mariana Trench in the Pacific is deeper than Mount Everest. So surely there is far much more water on the Earth, and therefore more drops, than there is sand. But now I'm going to take you through the maths, and it's much closer than I originally expected.
Also, you can hear about something so dangerous, a beam of light can make it explode. And we're talking all about rockets of the future, because they won't run on fuel, they'll run on plasma.
The energy source which heats up our own sun is plasma fusion. And so far, nobody has figured out how we can use fusion energy within a plasma rocket for the purpose of creating propulsion systems that might take us even outside of the solar system and out into the stars.
That's all on the way in a brand new Fun Kids Science Weekly. Let's start with your science in the news, then. And a critically endangered spider not seen in the UK for 40 years has been rediscovered. Aluonia albimana, which was last recorded in the UK in 1985, was found at the National Trust's Newtown National Nature Reserve on the Isle of Wight. It's been missing for 40 years and it's come back. It was spotted in a remote, overgrown area of the reserve that you can only get to by boat just over a mile away from where the former colony of spiders were. The team that found this tiny orange-legged arachnid have named it the white-knuckled wolf spider. They say it's a major conservation success, but they're a bit confused as to why it's out there on its own, close to where his mates used to live, but they're not there anymore. I love these brilliantly mysterious science stories, because you know that some experts out there, they're going to try and figure out the answer. Also, here's another mystery. The waters of the North Pacific Ocean have had their warmest summer on record, but experts don't know why. So sea surface temperatures, how hot it was on the top of the ocean between July and summer this year, were more than 0.25 degrees C above the previous high, which was a few years ago. That's a big increase. It sounds small, 0.25 degrees, but actually that's warm in Celsius. And that's across an area roughly 10 times the size of the Mediterranean Sea. It's huge. Now, climate change is known to make marine heat waves more likely, but this time scientists are struggling to explain why the North Pacific has been so hot for so long. And strangely, if you live in the UK, experts say this warm blob, all this extra heat, it might actually make the winter in the UK colder. Figure that one out, while scientists try to work out why that ocean's been so hot. And our final story this week, for the first time ever, some praying mantises have been spotted in the wild in parts of Cornwall. 2 separate sightings have happened near Truro and Moulsel, down on the southwest coast of England. It's strange and it's exciting. Should we find out why they're there? Dr. Luke Tilley is from the Royal Entomological Society. Luke, thanks for being there. Praying mantis is a creature that we hear a lot about, but they're so unusual to us in the UK. What type of creatures are they? Just describe them.
Well, they're a really interesting insect visitor to the UK now that we're getting sightings. And they are small. They come in various colours, but these particular ones are green, and they're sort of twig-like and look to blend in with the surrounding leaves and vegetation. But they're called praying mantises because they have these amazing front legs, which are folded round as if they're in prayer. So hence a praying mantis. But in fact, don't be fooled, because they are really good ambush hunters, and they use those front legs to grab their prey as they sit there and waiting to pounce in ambush.
Now, before we find out why they might be in the UK, where would we normally need to travel to see a praying mantis?
Well, you get praying mantises much more in the tropical regions of the world. A number of the species can fly, and they have really quite complex hunting behaviours and behaviours that allow them to find their food and themselves to hide from predators.
So there has been experience of praying mantises ending up over in the UK, but this has been found in Cornwall, the 2 sightings, I believe. Do we have any idea why they might be there?
Well, there's a few options. They could have been blown over from mainland Europe, where we do get praying mantises. Obviously, Cornwall is one of the warmer parts of the country, so they probably find it easier to live there because they can't really overwinter due to our frosts. It gets a bit too cold for them, and they are much better adapted to live in more temperate or tropical parts of the world. But also, praying mantises make quite popular pets. So you can buy them for pet, keep them in an insectarium, and feed them yourself and watch them grow and develop. So it may be that they've escaped from being a pet, or that they've drifted over, and we're starting to get these type of insects, these species, in the UK.
Well, hang on. You said that they might have been blown over. So a praying mantis somewhere in a warm part of Spain or something like that might have just hopped on a gust of wind?
A lot of insects, including praying mantises, use the air column to travel and to migrate. It can also just happen by accident. So insects are very light and they can get blown by gusts of winds quite easily.
Now, as the planet gets warmer, as we're in the middle of this climate crisis, ecosystems all around the world are slightly changing, and around the UK we are seeing different creatures be more at home because, as you say, it's getting a little bit warmer. So we've seen a few praying mantises. Might them being here mean that a few more are likely to be here? Will we see families and pods of these creatures?
We don't actually have any evidence that the praying mantis is breeding yet in this country, but we do have spottings and sightings increasing. So these 2 from this year add to about a dozen from that were already known. So they are increasing. So it's something to look out for when you're next out and about, because they're really charismatic little insects, and they're really noticeable if you have a look.
So what are the next stages there, Luke? So you're a part of the Royal Entomological Society. Knowing that these creatures are here, is there any work or action that you might take to try and make sure they thrive? Is it a case where you just kind of leave these creatures to be and hope they do well?
Well, I think it's not really either to hope that they do well or to hope that they don't arrive. It's just a symptom to show that climates are changing, and because insects are small and they are really mobile, so they can get about and fly often. Like I said, they can catch gusts of wind. They're a really good insight into how the climate is changing, how habitats are changing, and we can use our over 24,000 species of insects in this country to be indicators of how our world is changing.
Well, it's been really brilliant to learn all about the praying mantis, and you might see some if you're near Truro or Malsall down in Cornwall. Dr. Luke Tilley from the Royal Entomological Society, thank you for joining us.
Thank you.
Thank you so much to Luke for coming on, telling us all about the praying mantis that's been spotted. Very quickly, I want to give a huge shout out to Ted, who's down in Australia. Hey, Ted, thank you for finding the podcast and thank you for listening. We've got some questions now. If you have any question that you'd like sorted on the show, easiest thing to do, leave it as a voice note on the Free Fun Kids app. That way I can listen. You can star in the podcast and I can get a genius to answer it for you. You can do that on the Free Fun Kids app and at funkidslive.com. Love that every week. We've got a question here from the OG Etta. Etta, you're always sending in questions. They're always amazing. It's all about the most dangerous substance ever. Well, Etta, if something's dangerous, it has to be a dangerous Dan, doesn't it? And it is this week. So stick around. I will tell you more in just a sec when we officially get to Dangerous Dan. Let's get on another question before then. Here's Judy, who wants to know, what's the longest you can go without sleep? Well, the longest recorded case of a person staying awake was Randy Gardner back in 1964, so 60 years ago. And for a school science project, Randy stayed up as long as he could. He lasted about 11 days. How ridiculous is that as a school science project? That's your homework. How's it going? Yeah, it's all right. I'm a bit tired though. So I've forgotten to do all my other homework. Randy stayed awake for 11 days, so just under 2 weeks. And it's not good for you, really. After about a day, you've got impaired brain power. You can't think as well. You can't pay attention brilliantly, and you're moody, you're crabby. After 2 days, it gets worse. You hallucinate. You start to see things. Then long-term sleep deprivation causes heart problems, breathing problems, memory issues, harms your immune system, so you get sick. That's what happens if you don't go to sleep as often and for as long as you should. And Randy Gardner found out all about that. 11 days staying awake. Thank you very much for your question, Judy. Let's get on another one, shall we? Brilliant, it's a voice note. This is from Romy.
Hello, Dan. My name is Romy and I'm 7. My question is, are there more droplets of water in the world than sand? Thank you. Bye-bye.
Romy, thank you so much for your question, and thank you for all your questions, Romy. I love that you're always curious and you're always sending over stuff. Today, are there more droplets of water or grains of sand in the world? Wow, it sounds like a riddle that would let me get the gold from underneath the dragon, doesn't it? Is there any way we can work this out? Let's find out. Friend of the show, Dr. Thomas Woolley from the University of Cardiff, a mathematical biologist, is going to sort it out for us. Thomas, thank you for being there. There's a lot to this. How did you start trying to figure it out?
Well, it's such a great question because, I'll be completely honest. After doing all the maths, I still don't really know. This is the problem. When I first started thinking about it, I thought, well, surely there's much more water than there is sand. The Earth is over 70% water. The Mariana Trench in the Pacific is deeper than Mount Everest. So surely there is far much more water on the Earth, and therefore more drops than there is sand. But now I'm going to take you through the maths, and it's much closer than I originally expected.
Well, Thomas, let me ask you this to start with. A droplet of water. That's what Romy said. Are there more droplets of water? How would we figure out what a droplet of water is?
Oh, well, you've got to the crux of the problem here. How big is a grain of sand? What is a droplet of water? And those definitions of what we think those two are will completely change the answer to this question. So they are very crucial. So to be honest, I don't know. So what I did, as we all do, we go Google things. We go look. Who has looked into this? And there's a great website out there from NASA where they have quantified different droplet sizes. So droplets in a cloud, very, very, very tiny. Droplets that fall to Earth as rain, they're around about a millimetre, a tenth of a milliliter. So there are 10 drops in a milliliter, and that's what I used in my calculation.
Right, so 10 drops in a milliliter of water.
Indeed.
Run us through the rest of your calculations, because there's a lot to think over.
There really is. So, the first question is, how much water is there on the Earth? Again, I do not know this, but thankfully, there was the US Geological Survey that measured this, and they calculated that there is 1 billion cubic kilometres of water. An incredible. And now, one thing I would like to say here is that we do have words like 100,000, million, billion, but the numbers we're going to be dealing with are going to be so large that we're actually going to be throwing away these names. And I'm going to be using a terminology called the order of magnitude. So I don't really want to care about a billion having 1 and 9 zeros. I'm going to call that 10 to the 9. So it's a 1 with 9 zeros. 100 would be 10 to the 2. It's a 1 followed by 2 zeros. So if I were to throw that to you, what's 10 to the 6?
10 to the 6 is 10 million?
That's 1 million. It's 1 with 6 zeros.
Oh, okay, sorry. Right, all
10
right.
to the 6, no, that's great. 10 to the 6 is a million. So I won't be using the 100, the 1,000, because, like I said, the numbers we're going to be using are big. They're big. So a billion is 10 to the 9. 10 to the 9 cubic kilometers of water. Now, a cubic kilometer is a bit useless. We normally work in liters, so we can convert that. In my previous question, we were looking at the metric system. So going from cubic kilometers to liters, we convert that to 10 to the 21 liters. A 1 followed by 21 zeros. But again, we don't want liters, we want milliliters. So we multiply that by 1,000 because there's 1,000 milliliters in a liter. So at the end of all this, there are 10 to the 24 milliliters of water on Earth. And what I would say is that that's not accurate. No, there could be 3 times 10 to the 24 or 6 times 24, but we don't really care about that number. It's the number of zeros that's really going to change all of this. So order of magnitude, 10 to the 4, 10 to the 24. And as I say, there's 10 drops in a milliliter. So putting all that together, 10 to the 25 drops of water on the Earth. A 1 followed by 25 zeros. Huge number, huge number.
So that's our water. I'm just thinking, this is the perfect answer for a podcast, because when you're listening, you can skip back. You can keep skipping back just to really listen thoroughly and closely to all the different zeros, all the numbers, all the calculations. So we've got our 10 to the 25 amount of water.
Yeah, drops of water. Drops of water.
What were you thinking about grains of sand?
Similar idea. Again, I have no idea how much sand there is, but last year, in the Journal of Remote Sensing of the Environment, they took satellite data and mapped how much sand was in the deserts. Now, interesting point here, they only looked at the area covered by the sand. They didn't look at the depth, because you can't get that from a satellite image. So how thick are deserts? That's a very troubling question. I couldn't really find a categorical answer. Some people say some places it's 1 meter thick. Some people in other places say it's 50 meters thick. So again, I'm going to take a number of 10 meters as a rule of thumb, order of magnitude. So in total, there are 10 to the 14 meters cubed worth of sand in all the deserts on Earth. 10 to the 14. Now, we don't care about that. We care about how many grains are in there. So how big is a grain of sand? I have no idea, but the internet will tell me. I have a look, and there's a wonderful website from the University of Hawaii, which goes through all the different grain sand. So, there isn't just one grain sand. They're many different, and they all have different properties. So they have this wonderful website that tracks them all, lists them all. And so I'm going to take perhaps a slightly smaller size of 0.25 millimeters for a single grain of sand. Using that, I can calculate that as an order of magnitude that there will be 10 to the 11 grains in a meter cube. So 1 followed by 11 zeros. So we have 10 to the 14 meters cubed and 10 to the 11 grains in a meter cube. So putting those two numbers together, we add the numbers. So 10 to the 14, 10 to the 11. We add the 14 and the 11 to get 10 to the 25 grains of sand in the desert.
That's what we had for water.
Exactly. And do you know how furious that made? I was expecting so much more water.
So, I'm sorry, Thomas, have we had all those numbers? You've done all those calculations, and it turns out it's the same.
Based on the so whenever you get a number that's too close, you go back to your assumptions. Where have I made a mistake? And it comes down to these ideas of what is a drop, what is a grain? Because I took perhaps drops that were on the larger side of things. I took grain sizes that were perhaps on the smaller side of things. So if you perhaps massage those numbers a bit more, you do tend to get that there is more water drops than there are grains of sand. But if you wanted to swing the maths the other way, you would just take large drops and small grains.
Well, Absolutely mind-boggling. I'm going to need to re-listen to this about 5 times to 10 to the
I've
power.
had to do the sum 5 times just to make sure. So trust me, it takes that much time.
I'm going to have to listen to it 10 to the 50 times to figure it out. But thank you so much for doing the sums for us. So, Romy, there you are. Are there more droplets of water or grains of sand in the world? We're thinking droplets of water, but really, it could be up to you. Thank you for your question. And thank you much to Dr. Thomas Woolley for coming on and helping us out.
A pleasure. Thank you.
Thank you for that question, Romy, and thank you to Thomas for coming on the show and helping explain it. If you've got any question that you want sorted on the podcast, make sure you leave it as a voice note on the free Fun Kids app and at funkidslive.com. So we had a question a second ago, didn't we, from Etta, who wanted to know what's the most dangerous substance ever. So let's get to that. For today's Dangerous Dan, we're talking about something so small and so sensitive it can explode at any moment. Let's learn all about azidoazid. That's its name. It's a tiny chemical molecule, the formula C2N14. So it's made of a load of carbon and nitrogen atoms, a lot of them tightly packed together, squashed together. The problem is the bonds between those atoms, what links them, almost the hands that are holding each other, the bonds are very weak, and that's important, right? It was created by humans, not really found in the wild that we know of. But in 2011, a group of scientists in Germany announced that they had made this unlikely molecule, almost as a test, because they had the idea, they put it down on paper. They thought about the energy it could have, so they made it to see if it was possible. And it was. Azidoazid is 2 carbon atoms and 14 nitrogen ones. It's one of the most nitrogen-rich organic compounds ever made. Because of all that nitrogen, tightly packed but loosely bonded, with a small touch, with a tiny bit of heat, with friction or even a beam of light, it breaks those bonds apart and releases a huge amount of energy. An enormous blast. Many scientists wouldn't go near it, they say. It's thought to be the most explosive substance in history. And because of that, we don't really know what it looks like, because it blows up pretty much as soon as it's made. And that's why azidoazid goes straight on our Dangerous Dan list. But list might not be around for a long time. It might explode everything in it. It's time for Battle of the Sciences, where we figure out once and for all what is the greatest science to have ever existed. And this week, we're travelling far, heading way out through the universe. The big question is, though, how are we going to get there? Let's find out with Dr. Aaron Knoll from Imperial College London, who's talking all about space propulsion. Aaron, you have 1 minute to tell us why space propulsion is the greatest science of them all. And that minute starts in 3, 2, 1, go.
So my research deals with plasma rockets for spacecraft propulsion. So these are the engines that push around spacecraft and satellites once they're in space. So for example, if you want to go from the Earth to the Moon, or even further away, like Mars or the outer planets, Jupiter or Saturn. So in my group, we're particularly focused on using substances such as water in order to create a plasma. And for those of you who don't know, a plasma is sort of like the material which lightning is made of. So we generate a plasma using water, and then we act on it with electric and magnetic forces in order to create thrust for our satellites. So it's sort of like playing with lightning in a bottle using magnetic fields and using that in order to get us where we want to go in space.
Wow, there's your minute, Aaron. Thank you so much. So humans have been traveling through space for many, many, many years now. How have we improved the way that we propel ourselves through the universe? How has it changed in those years?
Well, when propulsion started, it used basically chemical fuels. So things like black powder in the very early days, all the way through to advanced propellants like hydrogen and oxygen propulsion used for the space shuttle. And nowadays we can use even newer materials such as xenon and krypton in order to create plasma thrusters for spacecraft, which allows us to propel ourselves much more efficiently. So we need to carry much less propellant with us into orbit.
So when you have this plasma, which is one of the four states of matter, and I think it's the most abundant, the most common, why is that particularly useful at moving us through space, much better than maybe chemical fuels that we would have?
Well, plasma is special in the fact that it can be acted upon by electric and magnetic forces. So rather than just having a hot gas and squirting that hot gas out of a nozzle, we can do something much more impressive with a plasma. We can accelerate it using electric and magnetic fields to velocities which are much, much higher than what you can get with conventional chemical propulsion. And for this reason, it's much more efficient at generating thrust in space.
Now, something like this must need to be brilliantly tested, because when it's up in space, it needs to work. What tools are scientists like you using to test out how efficient plasma is as a fuel?
Well, one of the most important things that we have are vacuum chambers. So this allows us to create vacuum conditions here on Earth by essentially sucking out all of the air from a container. And inside of that container, which is a very large volume, we can test our plasma rockets on the ground to understand how they're going to behave in space.
So it's a massive idea. But plasma works a little bit like lightning, and you say you're playing around with magnetic fields to make it work even better. What's the science behind that, as kind of simply as we can make it? Why do magnetic fields change how a plasma might work?
Well, the idea is you want to keep the plasma contained, trapped, for as long as possible so that you can heat up the plasma and then do something useful with it. So magnetic fields, if they're in the right configuration, can be used to trap the plasma for a period of time such that we're able to heat it up to incredible temperatures. And then once it's hot and very highly ionized, then we can act on that plasma with electric forces in order to do what we would like. And in this case, it's accelerating the plasma in order to generate thrust.
Now, Aaron, we always finish these chats in exactly the same way. Let me throw you forward years and years and years towards the end of your career in space propulsion. What's the one question that you really want answered? What do you want to know?
Well, I would say that the energy source which heats up our own sun is plasma fusion. And so far, nobody has figured out how we can use fusion energy within a plasma rocket. So one of the goals, long-term aims of my career, is to try to understand how we can use this sort of fundamental energy source in order to use that within our plasma for the purpose of creating propulsion systems that might take us even outside of the solar system and out into the stars.
And nuclear fusion, changing one element into another, yeah?
Yes, that's right. So for example, taking hydrogen, turning it into helium, there's a lot of energy released in that process. And that energy, if we're able to somehow harness it, can be used for the purpose of space exploration.
Well, will that field propel itself to the top of our Battle of the Sciences leaderboard? We'll find out. Dr. Aaron Null, thank you for joining us. Thank you to Aaron for coming on, talking all about space propulsion and why that's the greatest science. We can learn more about that now, actually. We're taking a trip to the smartest school in the solar system, Deep Space High, where Sam is making a presentation for his class all about spaceports down here on Earth and the type of craft that might head across the universe from there.
Deep Space High, spaceports.
Okay, everyone at Deep Space High, I'm ready to transmit my presentation on spaceports. You're gonna love it. Transmitting in 3, 2, 1. Since the early days of space flights from Earth, astronauts and objects have been launched using space rockets. You'll know what they look like. Vehicles with very powerful jet engines to escape the pull of gravity and stop them tumbling back down to Earth. As rockets have to carry everything with them, fuel, oxygen for both the engines and astronauts, supplies and command module, they are very big. The Saturn rockets that went to the moon in the 1960s were 363 feet tall, but the all-important command module with the astronauts in was much smaller, only 10 feet tall. Even the more modern Ariane rockets are over 170 feet tall. They're made up of a main stage rocket that burns for just 600 seconds and 2 solid boosters that burn for even less time, just 130 seconds before they fall back to Earth. A good thing about rockets is that they can carry very heavy loads, payloads of up to 20 tons. The bad thing is that, usually, they can only be used once, even the bits that fall back down to Earth. And with all the fuel they need, they're very expensive indeed. The space shuttle that NASA used until 2011 was designed to be cheaper to operate by being reusable. Whilst it launched vertically like a rocket, it landed like an aeroplane, gliding down to a runway and landing on wheels. It was really successful, and, as well as launching satellites, it played an important role in the construction of the International Space Station. The shuttle, though, was still expensive, costing $450 million each mission. And whilst it could be reused, it took up to 6 months before each one was ready to launch again, which is pretty inconvenient if you want to get out there and explore. To get around this problem, space companies have been developing a different type of spacecraft. A spaceplane. It's basically an aerospace vehicle that operates as an aircraft in Earth's atmosphere and as a spacecraft when in space. Spaceplanes can take off either vertically attached to rockets or horizontally on their own attached to a carrier plane. And however they take off, they return horizontally on a runway, the way a normal aircraft would. The Virgin Galactic is a suborbital spaceplane. It's not designed to travel into space, but to carry passengers to experience what spaceflight is like. It launches on a carrier plane called White Knight 2, which carries the spaceplane into the higher atmosphere from where it begins its space journey. As it doesn't enter orbit around Earth, it requires a lot less energy for propulsion and can use its wings to provide lift for its ascent. Virgin Galactic is designed to carry space tourists rather than deliver new satellites or provide supplies to space stations. Elon Musk's SpaceX program is developing a range of spacecraft and cost-efficient reusable rockets with the goal of sending manned missions to Mars. Rocket reusability is the key breakthrough we need to reduce the cost of access to space and enable people to live on other planets. Now, it's not quite like getting on a bus. The craft will still need weeks or months of repair and maintenance between flights, but it's much cheaper than building a rocket from scratch every time. Another good thing is that they use all sorts of airports, which means we can reuse existing sites rather than having to build new ones. So when the UK gets its first spaceports, you're much more likely to see a horizontal landing rather than vertical. But we'll be finding out more about that in my next installment. Losing the connection. Catch you next time.
Deep Space High, Spaceports. With support from the UK Space Agency. Find out more at funkidslive.com/space.
And that is it for this week's Fun Kids Science Weekly. Thank you so much to all our guests for coming on, and to you for being there, for listening, taking a trip to Deep Space High with me. Loads more brilliant podcast episodes like that you can catch up on wherever you get your shows, or on the free Fun Kids app and at funkidslive.com. If you have a question that you'd love to get answered, send it in as a voice note. Free Fun Kids app on the Fun Kids website too. And Fun Kids, we are a children's radio station in the UK. You can listen all around the country on the app, on our website, and if you've got a smart speaker, wake it up and ask it to play Fun Kids.